Hi folks, we're going to take a look at number 17 from page 180. So here this is a bit of a proof question. So they give some information about functions f and g. They tell us that f and g are both positive functions, meaning they're greater than 0 for all their domain. And they tell us that f has a local max at c and g has a local min at c. And they want us to show that this function created from f and g, so f divided by g, itself has a local max at x equals c. Okay. Now, when you're trying to solve a problem like this, the first thing I would suggest doing is figuring out what it is you actually need to show. So if h has a local max at c, it means that c is going to be a critical number for this function h. Okay, so the first thing we need to show is that h has a critical point at x equals c, and that can happen by either the derivative being equal to 0 or not existing at c. So this, I'll put this as in to show. Okay. So the first thing we need to do is to show that the derivative is either equal to 0 or doesn't exist at c. And the second thing we have to do is we have to show that there's actually a change in the increasing and decreasing behavior of the function. Now, since we have to show that it's a local max, means the function has to go from increasing to decreasing, okay, which means that h prime has to go from positive to negative at c, okay? If we can show these two things, then we know that we have a local max there. All right, so in order to do this, it all revolves around working with the derivative. So the first thing I'm going to do is find the derivative of this function. And of course, I'm just going to be applying the quotient rule. Now, I can't be working with a specific function that has these characteristics. I have to show that this works for any pair of functions that have these characteristics. Okay, so let's go ahead and find the derivative. Well, we know it's f prime at x times g of x minus f at x times g prime at x all over g of x squared. Okay, now we don't have to worry about anything with regards to this denominator here because g of x is strictly greater than 0. So this is never going to be equal to 0. All right. So let's start by showing that h has to have a critical point. Okay, so I'll call this 1 and I'll call this 2. Okay, so we see that h prime has f prime and g prime as part of the expression. So since f and g have local extrema there, in other words, have critical points at x equals c, since we know that they're local extrema, then it means that f prime and g prime are either 0 at c or they don't exist at c. Okay, so let's say we have f or g, or f prime or g prime, not existing at x equals c. Okay, let's say one of these or both of these things occur at c, then we know that h prime can't exist at c because one of these terms at least is not going to exist. Okay, so we can say then h prime at c does not exist. Okay, and what does that imply? That implies that c is a critical number, which is one of the things that could happen. Now, the other thing that can happen is that neither of them don't exist, meaning that they both have to be equal to 0. Remember, c is a critical number for f and g, so it means if either of them doesn't exist, the only other option is that they're both equal to 0. So if f prime at c and g prime at c are both equal to 0, well then what happens with h prime at c? Well, what do we have? We have f prime at c, which is equal to 0, times whatever g at c is. Who cares what it is? It's not going to affect my result because I'm multiplying by 0, minus f at c, who cares what that is, because I'm multiplying by g prime at c, which we know in this assumption here is going to be equal to 0, times g at c squared. Okay? And because the numerator is equal to 0 and the denominator can't be equal to 0, this is going to be equal to 0. Okay? Which again implies c is a critical number. Okay? So we've shown now, number 1, has been shown. Okay, because of the fact that f and g have critical points at C, regardless of whether it happens because one or both of the derivatives don't exist, or that the two derivatives are equal to 0, we see that in both cases, in this case here, the derivative of h can't exist at C, or it has to be equal to 0 at C. So it's a critical number. So now the next step is to show that the derivative of h changes from positive to negative at C. Okay, and what I'm going to do is I'm going to create a chart here. So there's my critical number, and I'm going to pick some number to the left of C, which I'll call A, and some number to the right of C, which I'll call B, and I'll make a little chart with F and G. So F has a local max at C. So it means F prime has to go from positive to negative as I move from one side of C to the other. And G prime has a local min, meaning the derivative, or sorry, G has a local min, meaning G prime has to go from negative to positive. All right. So what I'm going to do now is I'm going to evaluate, I'm not actually going to evaluate, but I'm going to determine the sign of H prime at A. So some value to the left of C. And what do we have? Well, let's remember what our derivative is equal to. This thing here. F prime at C, we just established, must be positive to the left of C. So I've got some positive number. But then I'm multiplying that by G at C. And what did we say about the function G? It's always positive. Okay, so regardless of what C is equal to, I know that this second term is going to be a positive number. Okay, minus. Okay, F at C, again, positive, times G prime at C. Hey, sorry, not G prime at C, G prime at A. Sorry about that, because I'm working with this side here, has to be negative. Okay, and of course the denominator is just some positive number. So what do we have here? We have a positive number minus a negative number. Okay, that whole thing is going to end up being positive over positive. So H prime at A is going to be, oops, sorry, some positive number. So if I look at H prime, it's positive to the left of C. All right, so again, just to repeat, I know this first expression must be positive, and I'm subtracting a negative number. So that's like adding a positive number. Now let's try to the right of C. Let's see if we can determine the sign of H prime at B. Okay, well again, F prime at B, we know has to be negative. Okay, and G at B has to be positive. So that's a negative number minus F at B. Well, F is always positive. Okay, and G prime at B, on the other side here, it's positive. All over G at B squared, which is going to be positive. Okay, and so now what do we have? We have a negative number minus a positive number. So that must be negative. And so that means to the right of C, H prime is, is negative. So what we've done is we've established that H prime goes from positive to negative at x equals C. And so now we've established both of the conditions needed for H to have a local maximum. Okay, it's got a critical point at C, and it goes from positive to negative. So here, therefore, H has a local max at x equals C. Okay, so let's recap, because this is a particularly long question. There was a lot to show, but let's try to break it down. So step number one, when you're trying to give a proof like this, you want to first establish what it is you have to show. What you have to show here in order to show a function as a local max is that it has a critical point there, because remember Fermat's theorem says that's the only place one can find local extrema. And because it's a local max, it has to change from positive to negative. Okay, so then I take the function that I'm working with and I use the info given in the question to show what I need to show. In this case here, using the fact that we knew that F had to have a local max there and G had to have a local min there. Okay, that's it for this one.